Hello and welcome back. In this final sub-module in the verification unit, we'll be looking at a few individual topics, more advanced topics related to verification. We'll first talk about assertions, then about formal verification, about the engines that are used for verification, and finally the role of system Verilog in system verification. First, look at assertions. The idea here is to actually insert code in your RTL, not in the test fixture, in the RTL, that checks for specific behaviors that you're expecting. These are usually used for fairly complex behaviors, such as interfaces, bus arbiters, things like that, things that can easily go wrong. The idea is to put it in your RTL code, but not to synthesize it. This doesn't become hardware. It's simply something that's put in there that asserts a particular property that we expect to see in the simulation. The system Verilog language, as we'll see later, actually has a very concise way to capture assertions, but they can also be written in normal Verilog. And here's an example in Verilog 95. What this is, as noted in the comment, and this is a good way of doing comments because it describes the functions, not the actions of the code. What we're doing here is there's a bus arbiter. We want to check to see that after one cycle, after any request occurs, it grants one and only one bus request. So first of all, some structure here. You notice we have an embedded synopsis directive in this comment. Remember, putting synopsis into a comment precedes giving synopsis a command. In this case, the command is quite simple: turn yourself off. So this is turning off synthesis. We can also use an if-def statement to turn off assertions. Here we're saying if there's somewhere else in the code, if assertions on is assigned to be true, then we actually want to run this code. If it's assigned to be false, then we don't want to run this code. And we have some comments. Then we actually have the behavior that we're asserting we want to see. That is, after a pos edge clock event, if any request line goes high and there's no active grant lines, and all of them are low, then we wait one clock period, then check to see that at least one grant line went high, and that only one grant line went high. If one of these conditions are false, then we report an error out to the display. We have an end if, so that this isn't run if assertions on is off. And then we turn the synopsis back on. We finish with the assertion. We want to go back to synthesizing the code that's being presented to design compiler. Later on, we'll see a simpler way to capture an assertion like this in system Verilog, but this can be quite useful even in this slightly more obtuse version as shown here. Next, I want to talk a little bit about formal verification. The idea in formal verification is to apply mathematics to work out to prove that some representation of the design is correct, or more precisely, as correct when compared with another representation of the design. They're usually used to check two different versions of the design. Formal verification is a little bit of a mixed reception in the industry. Some companies do use it and like it and swear that it saves some verification time. Other companies don't use it. It kind of brings up all the old jokes about mathematicians and engineers, about the precision of mathematics, but how difficult it can be sometimes to make it useful. For example, the joke that an engineer is in a balloon and he's lost and he calls out on the ground, "Hello down there, can you help me?" And the guy looks up and ponders and says, "Yes, I can." And the engineer yells down, "Can you help me? Where am I?" And the guy looks up at him and thinks and says, "You're in a balloon." At which point the engineer returns to his colleague and says, "Hey, he must be a mathematician. First, his answer was absolutely precise. Second, it was completely useless." Well, Formal verification sometimes has that reputation, but other companies do swear that it is useful. There's two main uses for formal verification, that at least as used commercially. There's more in research. The first is equivalency checking. That is, determine that two designs are logically equivalent. A good example of this, and a useful example of this, is comparing the RTL and the netlist. This doesn't tell you either are correct, but at least tells you that they're the same. And sometimes this is used if small non-code changes are introduced as well, to again verify quickly that the netlist you're producing is correct. Equivalency checking is relatively widely used because it's quite useful to know this, that the synthesis hasn't accidentally introduced a bug into the design. The only other way to verify this would be to do lots of post-synthesis simulation, which would be extremely time-consuming. Another less popularly used formal verification tool is what's called model checking. Again, this is comparing A versus B, but what we're comparing against is some higher level specification that's more abstract, hopefully mathematical in its representation, that specifies some properties of the design that we expect to see. For example, specifying formally a specific finite state automata, then checking to see that the design we've implemented matches that automata. Again, this is only as useful as the higher level design is accurate, and it does require a methodology and a suitable language for capturing that design. But there are commercial tools sold to do model checking. But again, equivalency checking is the most wide use of formal verification. What actually happens there, by the way, is that the RTL and the netlist are both reduced to a common logic denominator, specifying the logic contained within them. And this common denominator, based on a method called binary decision diagrams, are actually compared mathematically to show they're exactly the same. Thirdly, I want to talk just a little bit about the different simulation engines that can be used to verify a design. What you've been using so far is an event-based Verilog simulator. That is, it interprets the Verilog as it runs, keeps track of what gets triggered, keeps track of the signals that trigger it. This is very useful and very widely used. You can also buy what are called cycle-based simulators. The idea here is fairly straightforward. The Verilog is compiled into binary that can then be run in binary on the actual machine. Thus, it's faster, but a little less general. Sometimes not all the features are supported. Instead of just putting a room full of computers that use simulating Verilog, you can buy hardware accelerators that accelerate the functionality of the Verilog. This has limitations because you're limited by the I/O between the computer and the hardware accelerator, but these things do work. But of course, you have to keep replacing them as Moore's law keeps progressing. Finally, something that's very useful and actually quite commonly done is emulation. The idea here is, before sending the standard cell chip out to fab, build a multi-FPGA version of the chip. This might be a whole rack of FPGAs. The design is split up amongst those FPGAs using some partitioning approach. It runs much slower on the FPGAs than on the actual chip, and a fair bit of engineering has to be done to get the hardware interface. In fact, what is sometimes done is a rack of FPGAs is connected to a set of cables that are then plugged into the chip socket where the chip would go on the motherboard. Once you have this, you can actually run real code on this and do it much faster than you can on a Verilog simulator. So, for example, if you're building a computer, you could actually run real benchmarks on it, real applications on it, albeit at a much slower rate than would run on the eventual system. This gives you a high degree of confidence in your functional verification. And again, is quite commonly used, but does take a fair bit of engineering resources. This takes a couple of man-years to do properly for each individual design. Next thing I want to talk about a little bit of verification metrics, and we've already looked at this a little bit in particular code coverage. Now, how do you decide that your chip is ready for fabrication? You don't know that it's bug-free. You can't prove or otherwise demonstrate the lack of something. So in general, you want a metric that relates the costs and opportunity costs related to building the chip to the cost of doing more simulation. Right? So as you do more and more and more verification, eventually you in principle reach a point where it'll actually be cheaper and quicker to make the chip and find the remaining bugs on it than to keep doing verification. And a factor that comes into this is time to market. You don't want to do so much verification that you overly delay the introduction of your chip to the market and give your competitors a leg up. So there's constant pressure to reduce the design cycle. Metrics that can be used include a bug discovery rate. How many days have I gone without finding a bug in my verification suites? I've heard numbers such as once you reach 3 days without finding any bugs, you send it to fab. Code coverage is important. We talked about this earlier. How many lines have been executed? You at least want that. And if possible, you want a large percentage of the branches executed in it as well. Functional coverage. Do the intended functions that you must have actually run on the design? You can do this in high-level simulation. It is very time-consuming to do this. It's often done on a pseudo-random basis rather than running the complete function. So there's your sampling aspects of that function and running those. But it is a very useful metric. Assertion coverage. Are your assertions all telling you that things are running correctly? Sometimes some combination of these are used. Typically today, functional coverage is the main metric that's used. Here's a little more about these metrics. Code coverage. Has every line of code been simulated? You at least want that. And the idea here is there's instrumentation attached to the simulator that measures this. You also want to know what percentage of possible state sequences or paths through the design have also been simulated. You can't exercise all of these, but you want to exercise a large percentage of them. Functional coverage relates to the functions in the specification. Now, for example, have you simulated all the interface modes in the USB interface? That would make sense if you're selling a USB product. This is done in a system Verilog framework, as I'll show later. It can also be done by integrating via the programming language interface to a C-level version of the functions being done. This is a very popular metric today. So finally, let me talk about the system verification environment and use that as a motivator for the system Verilog or Verilog 2005 language. I'm only introducing you to the topic here. Again, at NC State we have a full course related to this that's offered in fall. EC 745 verification. The idea here is we have our device being simulated. There are assertions attached to this device, to this code. This is RTL code. We have, in yellow here, the golden model. This produces vectors for the design under test and checks the results against its own simulation of how the part should behave. The driver and the monitor provide that interface. A scoreboard is kept here. The scoreboard tells us what where we're at in terms of the simulation. How much have we covered? What functions have been tested? How many pseudo-random vectors have been tested? The test up here is creating the stimulus that drives the golden model, which is again in a higher level language, and also drives the detailed vectors applied to the device under verification. This is tied in with the concept of functional coverage. The idea is measure functional coverage, at least of a pseudo-random subset of vectors that can be functionally generated from the golden model. And in principle, this gives, and in practice, this gives a much faster convergence to low levels of bugs than other techniques, such as writing a successive sets of benchmarks to test different aspects of the design. What we mean by functional coverage here is these test results run on the golden model, produce a set of vectors that we test on the device under monitoring for the different functions that we expect to see as driven by the tester. Finally, I want to introduce System Verilog. This is a history of System Verilog, of Verilog standardization. We've talked about Verilog 95, the original IEEE standard. Verilog 2001 was a slightly improved standard. Then there was a lot of interest in a more sophisticated Verilog, a much more sophisticated Verilog that incorporated other functions. There were commercial enterprises that eventually led to standardization, to full standardization in 2005. So sometimes System Verilog is also called Verilog 2005. So a little bit of the structure here. First, I want to thank David Otero Synopsys who gave me these slides. Verilog 95 was a basic language for capturing hardware, including the RTL subset. So it included some basic data types, some basic logic structures, event handling to manage the simulation, and so on. At the same time, there was another language which we've talked about in the introductory notes called VHDL. VHDL, even at the same time, had other features in it that Verilog did not, such as strings, multi-dimensional arrays, languages that support assertions, and so on. In addition, of course, there's always been C, which, as you recognize, as you know, has a number of features in it that are not supported in Verilog, such as strings, pointers, records, or structs as they were in C, and so on. So for a long time, people were wanting to incorporate all these sorts of features into Verilog. Even in Verilog 2005, a lot of these features were left out. Yes, we did get multi-dimensional arrays, but other things that are useful programming structures weren't introduced. So finally, there is System Verilog, which incorporates structures in VHDL and C, and even more so. They also include structures found in C++, such as classes, methods, and inheritance. In addition, we include interfaces, which is a useful programming structure, and also some things were cleaned up in the underlying language. For example, instead of reg and wire, they can be replaced by a unified type called logic, which makes a lot of sense. So finally, we have this unified language. In that it's unified mainly in the sense it covers very sophisticated verification as well as RTL specification, including some enhancements to that RTL specification. Most of the language features towards the top of this page are there to cover verification, not to allow us to specify hardware. Here are some of the more designer-related features in System Verilog that are useful. For example, there's a new design construct called interface. This allows you in a interface module to specify all the features on a common interface structure, such as a shared bus. Previously, you had bits and pieces of the shared bus in the modules that used it. Now you can bring this all together in one place, and this could be quite useful to make a design that's more maintainable, and because it's easier to integrate other modules into this bus by using this interface specification for the bus, then rewriting the required bits of the bus in those modules that are integrated. As I mentioned a moment ago, there's also some simplified design syntax. For example, you can use a logic data type instead of wire or reg. No, frankly, the use of wire or reg is anachronistic. It's even confusing because reg doesn't build registers, and logic makes this all simpler. In addition, there's a simple assertion language built into System Verilog. Here's a simple example. There's this thing called property, which basically precedes the idea of specifying an assertion. This property also tells synopsis not to synthesize it. The idea is at a rising edge of the clock, if request rows, then what we want to see is within 1 to 3 clock cycles, that's what this is saying, the hash means clock cycles, that acknowledge rows. So it's asserting that we want to see acknowledge go high within 1 to 3 cycles of requests going high. This is a simple example. You can see that it's very concise, and thus it's very useful. And as I said, we have the full C++ language it is C++, for verification, including complex data types. So that ends this last final submodule related to verification. Some of the main things I looked at here were assertions, which you can write in Verilog 95, and they're a useful way for the designer to assert specific properties of the design that he or she expects to see to indicate the design is correct. Talked about verification tools, including emulation, in which you emulate the design on an array of FPGAs, and formal verification, where you use mathematics to prove that two designs are equivalent. Finally, I talked about System Verilog, which is a unified language for design and verification, and the subject of another class here at NC State. So that brings us to the end of this verification module. Verification is very important. You need to know your designs work, your modules work, before integrating them into the top level view of the chip. And you need to spend a lot of effort to make sure they work before sending a set of masks to the factory for fabrication. And in this module, we talked about a range of techniques that are useful to doing this, and at least motivated System Verilog as a unified language that, together with quite rigid methodologies to generate and apply test vectors, lead to a very high level of bug freeness within our designs. Thank you very much for your attention, and I look forward to seeing you in the next module.